Okay, well, thanks for that brief introduction. You're
Sure.
going to be taking part in the panel later on.
Yes.
So any questions to Chris, feel free to put those a bit later on. And our next guest is David Learmonth. Now, he's actually a project director here at the NEL, aren't you? But project manager rather than project director. But you're here really in a different role, aren't you? You're here as the vice chairman of the European Metrology Network for Energy Gases. And you and Chris giving a bit of background to these projects. So if you can tell us a little bit about your organisation, that would be fantastic, and the importance of it too.
Yeah.
Let's take that microphone.
Okay, as you've heard, I work for NEL, but NEL's part of a number of organisations, one of them being the European Metrology Network for Energy Gases. So I just wanted to introduce people to it who might not be aware of it and just show NEL in a wider context. Okay, so you'll all be familiar with statements like these. This is the European climate law, which puts into law their targets for carbon emission reduction to be climate neutral by 2050, and that's pretty much in line with where the UK is aiming for as well. So the question then it becomes, how can metrology support this energy transition? So there's a lot of challenges. Chris mentioned some of them there, looking at reliable measurement to deal with these new gases within transport, distribution, storage, etc. So there's a coordinated effort across Europe to try and meet the needs of the stakeholders and look at the best ways to deal with those metrological issues and move them on into standardisation. So you see here where the energy gases are used within factories and our homes, etc. Mainly at the moment, we're relying on the bottom, which is a natural gas, but we're gradually introducing hydrogen and biomethane. So what we're trying to do is move away from natural gas into other sources of energy. Natural gas is still going to be here for quite some time. So there's a lot of work that can be done to make that more environmentally friendly. Carbon capture and storage is one thing that's been talked about. We can also use it to create hydrogen, blue hydrogen. So it's not as good as green hydrogen, but it's a step in the right direction. Okay, so who are the EMN for Energy Gases? Well, it's a group of a network of NMIs across Europe, and you can see we've got good coverage in all the main countries across Europe. It says 17 members there, but we've just taken on board another member, the Italian INRIM, the Italian Metrology Institute has joined us as well. So we're well represented with all the NMIs across Europe. So what is the scope? It's really becoming a centre for energy gases. It's funded through Euromet, which is a European Meteorological Institute organisation, with a focus on energy gases, renewable gases, and also looking at measurement services across Europe for gas flow, gas composition, temperature, density, etc. Okay, so the EMN for energy gases started in 2019. We've had a few milestones since then. We've had a number of workshops, engage with stakeholders to understand what their requirements are. We engage with the European Parliament to feed back to them where the gaps in metrology are and the gaps in standardisation. And we've just recently launched a website. And just to say about the website, if you wanted to find out a bit more, there's information about the different gases and the different projects that are happening across Europe within these areas. There's information, there's a newsletter, and there's information about workshops, etc. if people want to get involved. So for our objectives, we're looking to engage with stakeholders and disseminate information from the various European research projects. There's a few here which the colleague might mention in their discussion. So there's things like decarbonising the gas grid, working on hydrogen vehicles, work on biogas, biomethane, and also some work on natural gas to try and make it more environmentally friendly. So we've also developed a strategic research agenda. So Euromet had asked us to develop a strategic research agenda to help direct and focus any research that they're funding. So we were instrumental in putting that document together, and I think it's just recently been updated, but if anyone wants to see it, there's a copy on the website. You can download a copy on the website. And also we're looking to maximise the impact of the research, so you can find out the outputs from the research. Again, the website's probably the best place to get that information. Okay, we're also developing an online measurement services platform, so not every country has all of the facilities required to carry out the necessary research. So there'll be an online platform coming on at the end of this year to let everyone know what the various NMIs have by the way of services and test facilities. And really just to try and bring closer working between the various NMIs across Europe and have a joined up approach to research. So we have stakeholders who feed into our policies. So we've got all the European international trade associations, energy gas producers, people from the transport and distribution sector, research labs, standardisation organisations are very important. We regularly report to them on what's coming out of the research, and they feed back to us where further work's required, and we also engage with policymakers and regulatory bodies. And there's some of them shown up here at the bottom. So that's really about it. If you want to find out more, if you want to get involved in shaping future research on energy gases, you want to find out where services across Europe might be available, if you want to have a look at the website, hopefully you'll find what you're looking for there, or you can email direct to our chair. That's about it.
Question or two for you already, actually, but if you take a seat so we can hear you on your microphone, put those to you, that would be brilliant. So thank you for that. So yes, just a couple of questions. So what are likely to be the future projects for your organisation?
So the next round of research, there are 2 energy gas projects. So obviously Euromet funds quite a number of projects, but specifically on energy gases, there's a big proposal going in for CCUS, which Gabriel, I know, is leading, is involved in. There's also another project on hydrogen and metrology for hydrogen. So that's the 2 main areas that the proposal's going into for the next round of research, due to start in 2022.
Carbon capture, there's one here. Is that going to play a much more prominent role, the carbon capture utilisation and storage?
I think it will, yeah. There's quite a gap between, using hydrogen and biofuels. We're going to be relying on natural gas for quite some time, so I think it's important that we make it as green as possible. There's a lot of work going on in carbon capture and storage, because there are a lot of challenges on the metrology side, which you'll probably hear a bit about from Gabriel today. But yeah, it's definitely a very important area, and one that's getting a lot of interest from the research on the research side.
Brilliant. Okay, well, you will be taking part in the panel discussion. Does anyone have any brief, quick questions for David before we carry on, just in relation to what you've just heard, the audience here? Got a couple online. We're happy to carry on. Great. Okay, so our next guest is Revata Seneviratne. Oh, I knew I'd get this right. Seneviratne. Thank you. So you are one of the Clean Fuels team, 15 years experience in the energy industry. You've been working most recently, do take the mic. Oh, hang on, keep it there for a second. On hydrogen field test standard for light duty vehicles. Now, I've been watching Top Gear's James May driving around London in his hydrogen car, but we're nowhere near using them routinely. And electric is way out there, isn't it, in terms of powering cars? And that's what you've been looking at. So if we're going to have hydrogen cars, we need to have refueling stations. We need refueling stations. We need some form of way of having pumping system standards. So that's what we're going to hear about now. So now you can take the microphone. Thank you so much, Revata.
Good.
Right, thank you, Sonia. Right, so this presentation is going to be hopefully about 20 minutes long, and we are basically going to talk about why we need to be able to accurately measure hydrogen dispense from refueling stations and the field test standard that NEL have built for this purpose. Okay. Right, so there are four sections for this presentation, and the first one is the need for the field test standard. Now, the UK government published the 10-point plan in 2020, which looked at the green industrial revolution for to try to achieve the net zero by 2050. And point number 4 of that plan was to look at accelerating the shift towards zero emission vehicles. The reason why this is important is because transport remains the largest carbon emitting sector for the UK economy, and cars and vans alone, as shown in this graph here, account for 70% of the UK's annual domestic CO2 emissions. So the government is looking at passing a mandate soon, which looks at phasing out the sale of new petrol and diesel cars and vans by 2030, followed by, from 2030 onwards, looking at cars and vans to have significantly zero emission capability, and by 2035 onwards, all cars and vans to be 100% zero emissions at the tailpipe. So now there are two ways of achieving this, and one is to use battery-powered electric vehicles, and the other one is to have hydrogen-powered fuel cell electric vehicles, both of which produce zero harmful emissions at the tailpipe. Now, the problem is that there are certain circumstances where battery-powered electric vehicles are not suitable. And these are due to, for example, the limited range of the vehicle, as well as the significantly long charging times for battery electric vehicles. So this is where basically fuel cell electric vehicles can play a key role, because filling up a car with hydrogen for a fuel cell electric vehicle is similar to filling up a car with petrol or diesel. Basically, within 5 minutes, you can fill up a car with hydrogen and have about 400 miles of range. However, as Sonia mentioned, James May told in his YouTube video that he's got the latest Toyota Mirai car, got a good range, but there is a big limiting factor, and that is the fact that the UK, as shown on this slide here, does not have a refilling infrastructure for hydrogen refilling stations. And part of that is due to the significant barriers that are in place for dispensers to be installed. And one of the barriers is the issue that it's not possible to accurately measure or quantify to a sufficient degree of accuracy the amount of hydrogen that is dispensed from the refueling station. And if you can't quantify the amount of hydrogen that's dispensed, then the customer can't be charged correctly, which has a knock-on effect on the station owners, the hydrogen producers, and ultimately the UK government, because the government can't charge the correct amount of tax. So this image here basically shows that UK at the moment has less than a dozen refueling stations for cars. You've got 2 in Aberdeen, and that's all that you've got in Scotland, for example. Right? Now, there's been a lot of research that has gone into how do you safely refuel a hydrogen fuel cell electric vehicle. And most of the systems that are in place for refueling stations are based on either SAE standards, CSA, or ISO standards. Hydrogen is stored on board the fuel cell electric vehicle in what's called a compressed hydrogen storage system, where you've got hydrogen tanks, you've got the required tubing for it, then on-tank valves and so on, which makes sure that you essentially have a safe system for storing hydrogen. But one of the concerns when you look at filling up the car with hydrogen is that there is the heat of compression effects, which causes the tank temperature to increase. And there are systems in place which minimize that. So basically, hydrogen refilling dispensers follow what's called the SAE JS2601 protocol, which minimizes the tank temperature so that it's below the maximum temperature limit. Now, the accuracy for the dispensers that dispense hydrogen are specified according to the ORIML R139 standard. And based on this standard, you have got the maximum permissible error, which is 1.5% for the for the measuring system, that is the flow meter. And for the complete system, it is up to 2%. The problem is that it's quite difficult to achieve these targets because the hydrogen that's supplied can vary significantly in pressure from up to about 875 bar. And also, as I mentioned previously, because you want to minimize the temperature at which the hydrogen in the tank increases while pumping up to 700 bar, hydrogen needs to be pre-cooled to minus 40 degrees C. So based on these large varying conditions and in terms of pressure and temperature, Coriolis meters have become the preferred choice for dispensers. There are two common locations that are shown here. One is upstream of the pre-cooler, and the other one is downstream of the pre-cooler, and basically in the dispenser itself. Now, there are advantages and disadvantages to each. Installing the flow meter upstream of the pre-cooler means that you are basically measuring hydrogen at near ambient temperature. Okay, so it's quite good for the Coriolis flow meter. However, because you've got a large dead volume that's downstream of the flow meter, but basically you have measured that amount of hydrogen, but that amount of hydrogen hasn't been actually delivered onto the car, you have got uncertainties in the flow measurement itself, or rather in the amount that's dispensed to the car. So the one way of overcoming that is to install the flow meter downstream of the pre-cooler, where you're minimizing the dead volume. The only issue with this is that because the flow meter initially will say hydrogen at ambient temperature, and then the temperature drops significantly to minus 40 degrees C, this large change in temperature can affect the flow meter's accuracy. So based on these questions, MPA project MetroHive 1 was started to look at addressing some of these answers, some of these questions. Yeah. And what has happened recently is that we've just begun MetroHive 2 project earlier this year, which looks at the learnings from MetroHive 1 and continues to help with trying to solve some of these issues. So one of the aims of MetroHive 2 project is to develop a metrological traceable framework for testing hydrogen dispensers. And as part of this, basically the different measurement institutes that's taking part in this project are looking at having intercomparison tests where all the institutes take their field test standards to a single refueling station and have an intercomparison test. So TÜV Süd National Engineering Laboratory is participating in this MetroHive 2 project, and the funding for building the hydrogen field test standard was provided by BIS. Right, we shall look at now how we've gone about designing and building the NEL hydrogen field test standard for light-duty vehicles. The design basis for this field test standard was that it needs to be suitable to accurately measure the amount of hydrogen that's dispensed from the refueling station with respect to the ORIML R139 requirements. So the field test standard that we have built is based on the experience that other NMIs have gained during their construction and testing of their field test standards. And it is a gravimetric system that we have built, and it has got a hydrogen capacity or capability similar to a fuel cell electric vehicle. So basically, we can fill the hydrogen field test standard using the H70 dispensers and can fill it up to 700 bar, and according to the SAE 2601 protocol. The mass of hydrogen collected is around 4 to 6 kilograms, and the uncertainty of this measurement is about 0.3% at 95% confidence. Now, as you may know, hydrogen has some issues with, or has some concerns with regards to safety. So basically, because of that, we've done a number of safety studies to make sure that the system is safe to use. And the first one was obviously to conduct a hazard and operability study at the design phase. Then we went on to look at the hazard area classification study and an explosion protection document to make sure the system was safe to use. Now, because we're dealing with a system that is up to 700 bar in pressure, we have to also meet the requirements set by the pressure system safety regulations. Since hydrogen is a flammable gas, we've also got to meet the requirements set by the DESIR regulations as well. In addition to these, we've also undertaken risk assessment and prepared work instructions on how to operate the test rig. So how we would carry out the test is that the field test standard is transported in the rear of a van to a hydrogen refueling station. The van parks next to the dispenser, similar to what you would do if a fuel electric vehicle parks for refueling. And basically, you connect the dispenser straight on to the field test standard. Okay? The hazard area classification study had shown that you need to have a 5-meter safe distance for any piece of kit that is not ATEX certified or has some sort of, say, for example, the emission stack, which basically will be 5 meters away from the field test standard. We are also looking at establishing an exclusion zone for safety reasons and with suitable barriers and signage. Right, this is a schematic diagram showing the key components of the NEL hydrogen field test standard for light-duty vehicles. And as you can see in this diagram, I hope there's a point in here. Is it the middle one, is it? That's not right, by the way. Okay, right. So the dispenser nozzle connects directly onto the H70 receptacle, just like what you would have with a fuel electric vehicle. Then the hydrogen gas has the option of flowing directly past the Coriolis flow meter into the 2 tanks here. The system also has on-tank valves for each tank, and these tanks are the same system that's in place for, oops. Ah, that's okay. Right. Right. So the on-tank valves are the same system that's in place for a fuel electric vehicle. Basically, they activate if the tank temperature reaches 110 degrees C. Now, how you would operate this test rig is that it's a gravimetric system. So you take the mass of hydrogen, or sorry, measure the total mass of this setup that's shown here before filling and measure it after filling and look at the difference in weight. So once you finish that final measurement, then you need to blow down each tank. And how you would do that is you have basically 2 pressure regulators in series, which allow you to vent the hydrogen from the field test standard. There's a pressure relief valve also on the venting panel, which essentially limits the tank pressure to 20 bar, right? So this is to both protect the tanks as well as the hydrogen refilling station dispenser doesn't allow filling as part of the protocol if the tank pressure is less than 20 bar. Right. So as I mentioned previously, the light-duty hydrogen field test standard is a gravimetric system. So now the reason why we have gone with gravimetric is that what you got to bear in mind is that when you fill a car with petrol or diesel, you're measuring the amount of fuel dispensed in liters. Hydrogen being a gas, you need to use kilograms instead, okay? So we are going to compare essentially the kilograms of hydrogen that's dispensed as indicated by the dispenser against what we measured by the field test standard. And as I mentioned previously, is looking at the difference in mass before and after filling. So the gravimetric system basically consists of an ATEX rated multi-tariff weighing scale that has a 300 kilogram capacity and an indicating system that is on the DAC panel. The amount of hydrogen that can be measured before and after filling is basically 6.2 kilograms. It's the maximum capacity that is similar to what you've got in a fuel electric vehicle. And the empty mass of the field test standard is 280 kilograms. The scale resolution has been enabled by using 10x mode. You've got a 0.1 gram resolution on the scale. Metrotelido calibrated our scale for its maximum 300 kilogram span using 10 kilogram M1 class weights. And we also calibrate the scale before testing at a refueling station by using F2 class weights up to 7 kilograms, i.e. covering the full span that we are going to be using in terms of filling the tanks with 6.2 kilograms of hydrogen. Right. So now what you've got to bear in mind is that the hydrogen tanks we're using are the same tanks that are in a fuel cell electric vehicle. And those tanks are what's called a type 4 hydrogen tank. And they can expand slightly because of the 700 bar pressure. Okay. So you've got to make, because you're using gravimetric system, you've got to take into account the effect of buoyancy because of the tanks are expanding slightly. Right. And as a result, we've got ATEX rated temperature, humidity, and ambient pressure sensors that are able to measure the ambient conditions around the tanks and thereby calculate the air density, which then is used to make corrections for buoyancy. Also, what we've got is a nitrogen panel that is installed on the next to the field test standard as shown on the bottom right image. And the reason for the nitrogen panel is that after you finish testing, then you need to purge the tanks from hydrogen so that you've got basically less than 4% hydrogen in the tank. So it is safe to transport the field test standard back to our site over here, as well as you've got to maintain about 20 bar or more in the tanks because the tank cycle life gets affected if the pressure decreases below 20 bar. Right, we shall now look at the planned verification test for the gravimetric system. So it's important that we verify the field test standard before it is taken to hydrogen refueling station sites. And the setup that we're going to be using for this verification is basically similar to what other measurement institutes have done for their field test standards. And for this, we are going to be using nitrogen gas. So the protocol for validating this refueling station field test standard is basically first calibrate the Coriolis flow meter that you have on the field test standard. So you take it out, calibrate it at our nail test facility. And then at the flow rates that you're hoping to use for the verification test. Then in step 2 would be to install this Coriolis flow meter back on the field test standard, pass nitrogen gas at the flow rates that are within the flow rates that you have decided based on the calibration of the flow meter, and basically compare the results from the flow meter against the mass that you have calculated based on the gravimetric system. The verification test will be undertaken for the minimum measured quantity that is specified in the ORIML R139 requirements, as well as we are going to be looking at pressures up to 40 bar, which is about 3.6 bar of 3.6 kilograms of nitrogen inside the tanks. So we've done the calibration of Coriolis flow meter last summer, and this is the setup that was used. It is similar to the setup that was used previously in the MetroHive 1 project, where we looked at alternative methods for verifying Coriolis flow meters that are used in hydrogen refueling station dispensers. And basically what you're looking at is a setup that uses a Nel wet gas facility where we sent nitrogen gas at 40 bar through the flow meter at 20 degrees C and saw how the flow meter performed. As you can see on the bottom image there, the graph shows that the FETA standard Coriolis flow meter is very accurate with accuracy with a measurement uncertainty of less than 0.2% within the flow rate that we're hoping to use the flow meter for the verification test. So the setup that would be used to validate the gravimetric system is similar to the setup that was used for calibrating the flow meter. Basically, we're going to be using nitrogen at 40 bar or up to 40 bar at 20 degrees C. And in order to make sure that we have got 20 degrees C of nitrogen coming in, we have taken the nitrogen panel that was on the field test standard out and installed, or hoping to install it upstream of the heat exchanger, thereby ensure that you've got 20 degrees C nitrogen gas that enters the Coriolis flow meter. Right. The final slide is going to look at some future work that we have planned for NEL in terms of hydrogen refilling stations. So the first one is going to be the Metro Hive 2 project, as I mentioned previously, is whereby basically we're hoping to join up with the other project partners for Metro Hive 2 and verify each field test standard at a single refilling station and thereby have some intercomparison results so that we have got additional traceability for the NEL hydrogen field test standard. The next one is that TÜV National Laboratory are looking at launching a joint industry project in early 22 to determine and verify the performance of hydrogen refilling station dispensers in the UK in relation to the ORIML R139 requirements. And based on these tests, we're looking at compiling an best practice guide for the industry for verifying hydrogen refilling station dispensers. And as you might know, the UK, some of the councils in the UK are looking at heavy-duty hydrogen-powered vehicles for in terms of the council vehicles, right? And therefore, there is a need for heavy-duty field test stand as well, in addition to the light-duty one. So based on this requirement, NEL is currently developing a field test standard suitable for heavy-duty vehicles. And the design of that standard is based on the learnings that we have gained while developing or designing and building this light-duty field test standard. So the total mass that will be collected in the heavy-duty one is going to be 24 kilograms, and rather than 700 bar, heavy-duty standard is essentially for 350 bar. And the target measurement uncertainty is 0.5% at 95% confidence. Yeah, and that's the last slide. Yeah.
Excellent. Thank
Thank
you so
you.
much. That was really, really interesting. And we have got a couple of questions as well. So take a seat. But any brief ones from the audience at this stage? Yes.
It's on the complete batch. Yeah.
Okay. Anything else from the audience? Okay, we've got a couple online for you. How long does it take to carry out one test at a
Right.
hydrogen refueling station? So,
Okay, so that's a well, let's just say it depends on the type of test you're conducting. So therefore, it could vary between, say, to take a couple of days essentially, because you've got to bear in mind is that the actual filling of the standard is according to, say, protocol, and that is within 5 minutes. But what you've got to bear in mind is that there is additional requirement for basically verifying the gravimetric system, which can take some time. Then the biggest time-consuming part of the testing would be blowing down the tanks after testing, because there you've got to make sure that the tanks don't decrease too fast, otherwise it affects the tank's life, cycle life. So it can take up to 2 hours, 1.5 to 2 hours to do that. So based on the type of test that you're doing, it could take 2 to say 5 days, depending on the number of repeats and so on that you want to have.
that's how many tests can be done in one day?
Right. So again, it depends on the type of test you're doing, because if you're going with, say, for example, the full tank, then you're looking at 1.5 hours per test to deplete, right? While if you're looking at basically doing a minimum measured quantity only, which is 1 kilogram, then you can blow down the tanks much faster. So you can do a greater number of tests. So at the moment, because we haven't actually tested the system at refilling stations, we can't say the exact number. Yes.
So how does HRS get hydrogen, and what is the cost for building one? Always.
Right. So that one basically is tricky. So let's just say that there are 3 methods where you can get hydrogen to a refilling station. One is you can have gaseous hydrogen delivered by tanker. Second one is you could have hydrogen, which is in the liquid form, delivered to the refilling station. And the third one is that the station itself could produce its own hydrogen by having a solar panel or a wind turbine, right? So the cost of the station depends on the type of technology they're going to be using, right? So at the moment, the figures for that are in terms of a study at the moment only, so I can't give the exact amount, but basically they depend on the type of technology that's being used.
Okay, all right, brilliant. I was just checking if we had some more. I don't think we have. Oh, one more here on what is the uncertainty of the HFTS gravimetric system and what contributes to the maximum uncertainty?
Right, so our target uncertainty for our system is 0.3%, and we are hoping to verify that during the intercomparison test that will be conducted with the Metro Hive 2 project. The biggest contributor to this uncertainty is the gravimetric measurement itself, right? So that is close to 50% of uncertainty comes from that. And then the next biggest contributor is the measurement of or quantification of the air density. Okay. But again, it'll all be verified during the verification test and the validation against other NMI's filter standards.
Okay,
I've just
Chris has got a question here
yeah,
as well.
Just got one question. Thanks for the presentation. That was really interesting. In terms of the measurement challenges, now you mentioned that there's 2 potential locations for the Coriolis meter, before the filler and after.
Yeah.
And there's 12, I think you said about 12 refueling stations in the UK.
UK,
Do you know
yeah.
what the most common setup is? Is it for it to be before or after?
No, unfortunately, we haven't contacted those. Hopefully that's part of the next JIP would be to contact these refueling stations.
And if you were to guess, obviously maybe not so much guess, but do you have an idea of what one do you think would be more challenging before or after? Because I think you said the one after have a wide range of temperatures and pressures, which potentially affect the Coriolis meter.
The meter as well. So the thing is, it's again hard because we haven't done any testing. Basically we can't say which one is the more difficult sort of method or more difficult system to validate. Yeah. So Leon here is who is trying to lead. Yeah.
Match that number. Any transfer standards. All those.
Right. So what you're looking at is you've got the field test standard here, gravimetric system. If we can set it up such that you could have the Coriolis meter which you've installed, get that verified. So the ideal situation would be you first verify the gravimetric system at a refueling station. Then you would look at if you were to use the Coriolis flow meter as a transfer standard, right? That way, then you could speed up the whole verification of the refueling stations. So it's part of the Metro Hive project. Metro Hive 2 is to look at this whole setup. And so it's still in development at the moment. So, yeah.
Okay, we've got a couple more from the back there as well. If we can take those, if you can say who you are and speak loudly, that would be great.
Good question. I'm not aware of any, but then again,
part of the GIP, we're going to be looking at rising and up.
Got a follow up over there.
Okay. Okay, thank you. Right, on Coriolis vehicles, what the reasons standardizing on that technology and are we looking at?
it was, I suppose there would be like, it came from the Metro Hive 1 project where that was what most suppliers or most sort of companies had gone with, right? So the measurement institutes then tended to stick with that. But again, not too sure if there has been any one. No.
I've got a couple brief ones online for, I think we do, there will be an opportunity to ask some more a bit later on. So if I put these two and then we'll have a break. So do save any questions you've got now and we'll get another opportunity to put them later on. But a couple online. Is any work being carried out on reducing the venting of hydrogen from the HFTS?
Unfortunately, can't answer that one. I don't have any.
Okay, maybe that's what I'll comment on. It's something that at the moment we don't. Grand scheme of things. Is on our radar. At the moment it's just did that. So actually a small thing.
So, okay. You'll have to come over to the microphone. So Martin is well, he's going to let him do it himself if you want to. So
Yes, I'm Martin Hanson. I'm the technical director at NEL, overseeing these projects ultimately.
later. So there you go, Martin. Thanks for contributing to that. I think we can probably take our coffee break now. But I said if you do have any other questions, we'll get an opportunity to put them at the end in a Q&A. So please, don't forget them and don't feel you haven't got another opportunity. And same with our online audience as well. So we're going to hear about the next two projects straight after that coffee break. So join us, I think, in half an hour at next door. Wander back in.
Thank you.
Projects to hear from, and this time just a sort of brief. When I ask for questions, I will be going around with the microphone. Oh, I can take this off now, can't I? I'm pleased to say. So our online audience can't hear the questions. So before you talk, I'll be racing around with the mic for you, but we do still welcome those questions. So hopefully that will solve the problem for our online audience. So part two, if we're going to reduce greenhouse gases, we need to do something about carbon capture. Now, at the moment, the UK has no significant carbon capture storage plan. At least I think that's still the case, unless anything's changed in the past couple of days at COP. But I think that is about to change too, and it means we also need ways to measure how that carbon is captured. Now, that's where Gabriele Chinello comes in. He's head of carbon capture, utilisation and storage. And he's also developing a facility here at NEL, which verifies the tools used to measure carbon capture. Gabriele, please take the floor and tell us more.
Thank you, Sonia, for this nice introduction. So the pointer, there you go. Oh, that's the other way around. Okay, so I'm quite of a technical person, but I've tried to remove the technicalities from this presentation and make it available for a wider audience. So I've prepared a couple of slides, a few slides on carbon capture and storage, and in particular the role of flow measurement in enabling net zero. So we are all known quite aware that global warming is a direct consequence of carbon capture, carbon dioxide emission in the atmosphere. So there is a direct relation between the two. If we want to put a cap to the increase in temperature, we also need to put a cap in the amount of CO2 in the atmosphere. What's going on here? Yeah, that looks now is stable. Yeah. So in this graph, you have on the y-axis the temperature change, and on the x-axis you have the carbon dioxide emission. So we need to put a cap on CO2 emission, and I'm kind of trying to to show the concept of net zero and what CCS is with a bit of an analogy. So the cap is basically the level of your bathtub, and we are all sensible people. We generally not overflow the bathtub, but I have twins at home, 2 years old, and they like to go around the house and make the best of it. So one thing is they like to play with water, we all know, and put some toys in the bath. So they open the tap, and maybe, you know, I'm not aware of it. And that's what happened. And go up and up. And at a certain point, you reach almost the, you know, to overflow your bathtub. And that's generally the time when I came into the bathroom. And what do you do at that point? You know, you have sensibly the first things you do, you close the tap. You know, you don't want to overflow. But there is another little problem. My wife always told me, you know, the bath is leaking. You need to repair it. 50 years ago, he started to tell me this, but I didn't do anything. Somebody will make something at some point. It's not my problem. So the bath is leaking, and then I have another problem. It's still going to overflow. What I'm going to do? Well, the next sensible things I would say is to open the drain as quickly as possible. So this is a bit of an analogy. I mean, I kind of make a bit of entertainment here, but the subject is deadly serious. You know, we are not really playing here. We are really, you know, endangering our species in some way. But it's not that easy. But CCS can be considered our drain, basically. And that's the analogy is to tell you, as to tell the audience that CCS can be considered our drain in some way. And here is the net zero target and the net zero concept. So when people ask me, what is CCS? I generally say CCS is the word net in net zero. And I'm trying to show this here. So if you have a zero emission, it means you don't have any flow from your tap. That's fine. That's the best case scenario. Still, you have your bathtub full of CO2, right? But when you approach net zero, it means your tap is still leaking, but you are draining the same amount of flow. So overall, this is net zero. So the mass balance is zero, but you're still emitting something here. And that's probably our case at the minute. So the net zero target, that's what it is. You know, there are some countries around the world that are committing to the net zero target by around mid of this century. UK is one of them, and is actually in the law. And we are committing to net zero by 2050. Oh, sorry. So, which is the role of CCS in reaching net zero? Well, we have several sources that speak about the importance of CCS. I just put 3 of them here, but you can find many more in the literature. So Climate Change Committee, CCS is a necessity, not an option. So that's pretty clear. Also, the IPCC report, they envisage different scenarios to reach net zero. And in many of them, the majority of them, you know, the contribution of CCS was very relevant. And also we have the International Energy Agency that predict in their sustainable development scenario, they predict 10.4 gigaton of CO2 is captured from the energy sector by 2020. So that's not a trivial amount. So that means we really need a lot of facilities. Which is the UK government strategy? Well, again, CCS play quite of a role in the UK government strategy to reach net zero. We recently have confirmation that 2 clusters has been selected for track 1. So they are in negotiation with the government to receive support from them. Also, CCS again has important building block in the hydrogen strategy. So to have a rapid upscaling of low carbon hydrogen via steam methane reforming. And also about policy, at the minute they are looking to develop a UK emission trading scheme. So, okay, that's nice. I spoke about net zero and CCS, but which is the role of flow measurement, all of this? Well, we will need to mobilize large investment here. It's huge amount of of investment, both from public sector and private. And to build this infrastructure, somebody is talking about a green revolution. So again, it's not a trivial effort from everybody here. And when you start to mobilize money, you have financial transaction, you have goods transaction, and all these transactions are always underpinned by two things: quantity and quality. Doesn't matter if, this goes back centuries ago. It doesn't really matter much about what you are exchanging. It can be tomatoes and can be gold. It of course is changed the uncertainty, the accuracy that you need, but still you are always looking for quantity and quality. And again, I go back to my babies. They really like banana, and they already can say if I gave them 2 bananas or 3 bananas. So we are instinctively can recognize the quantity of things. And also they can recognize the quality, because when I give them the darker one, they generally don't want that. So for them, that's not good quality. Now, what about flow measurement? Well, we are interested in quantity. So since we are dealing with fluid, we need to measure the flow. That's where flow measurement goes in. And also about the quality. So this is an example of the CCS chain you can have across the country. So you have the capture plant, you have the emitter, you have the storage, the CP loading, offloading. And I've tried to put the possible meter relocation. You see here with the M in the purple circle. So these are all meters that can be possibly be installed to measure the amount of flow going in and out from all these facilities. And that's really a key piece of equipment. And when we speak about measurement, we intend both the flow meter, but also the composition is a key element. So the quality of what we are moving. And that's, again, is important for payment between parties, process monitoring and control, and ensure compliance. And it's also very relevant for, payout of incentives from the government. You need to have something like this that show that what you are capturing or what you are storing. So how do we verify these meters? Well, that's really the tricky point, and that's where NEL comes in. In particular, it should be noted that you don't have the same condition at all of this point, right? So that will make our life easier if we have the same condition around the same. But you may have like something at high pressure, high temperature, something at low pressure, low temperature. It really depends on your project. And another important consideration is composition. That's of paramount importance. And again, at the minute, the composition of your stream is really project dependent. So there's not really a standard across the industry that says these are your composition requirements. So this is a bit of one challenge that we need to address. And I've plotted here just to give you a visual representation of pressure on the y-axis, temperature on the x-axis. And these are all the operating envelope, let's say, of some of the projects out there. And you can see again that we have 3 major regions. The gas region, you have the liquid region at low pressure, low temperature. You also have the liquid region at high temperature. So this is dense phase. And also some projects are also looking to go to supercritical phase. So this really, telling us something, because we have liquid, we have dense phase, we have gaseous phase, we have potentially supercritical. And the meter should work with this condition, this condition, this condition, and this condition. That means we need to validate the meter for each of these conditions. And that's our challenge. At the minute, there is a huge gap in traceability. It means that we cannot really validate and calibrate the meters that you are going to install, because we are lacking the calibration loop. We are lacking the traceability necessary to do that. And traceability is a key element, because it's basically give you certainty of your measurement. And that's what the business need, and that's what we really need. So in order to fill this gap, we are actually looking at developing facilities at NEL to calibrate these meters. And we are looking to split between gaseous and liquid flow loop, so to have two different approach. And for the gaseous loop, again, we are trying to cover this range, particularly the gaseous range. For the liquid, we are trying to cover the two ranges, the two regions that we are interested in. So low pressure, low temperature, and high pressure. Let's say medium temperature, medium high temperature. And this is underway. The gaseous loop is a bit more advanced, but liquid loop is very relevant. So both of them, we are really looking forward to proceed with this project. Also, we have a collaboration with Heriot-Watt University. Johnson is just sitting here, so if you are interested, he's the PhD student taking care of this project. And this project is about flow measurement with different mixture compositions, and we are looking to test Coriolis and orifice meters here. And it will be probably more dedicated to the dense phase and supercritical phase, but also on some extent on the gaseous phase. And this is the flow loop. It has a primary gravimetric standard. So we can test meter here with different composition to assess their capabilities. We will also we plan to test this meter also at NEL with different fluids like nitrogen or water, and also to investigate the transferability of calibration. We are also part of a bigger project, a European one. This is called Metrology for Decarbonizing the Gas Grid, or DECARB. And we have several working package here, not only from measurement. There is also a working package about equation of state, composition measurement, and so on. But NEL is mainly involved with the working package one. We are the working package leader for that package. That's about flow measurement. This project is not only for CO2, it's also for hydrogen application and hydrogen methane blends. We have several tasks in working package one. So task 1.1 is basically understanding the requirement of industry. So that's pretty important key, because if we don't get right what the industry requirements are, you're not going to meet the demands, the requirements. So we are really reaching a lot of stakeholders there, and I really appreciate if you want to engage with us on telling us which are your requirements, both from the manufacturing perspective or also from the operator's perspective. Then we have task 1.2, development of traceable facilities. We have several partners taking care of that. Task 1.3, we will test meters with hydrogen and hydrogen blends and see their performance. And also task 1.4 is dedicated to CCS. We will test flow meter, but with CO2, primarily with gaseous phase, but also some small tests with the liquid and dense phase. So that's the European project currently underway. As David said, we also have another proposal going on with a lot of different partners involved, and we will know the results in a few months' time, but that will be specific to CO2. So to end up, if you are interested to take part of the European project, you are really invited to take the survey on CCS. We really need your input. I think this is honestly a big challenge for all of us to, decarbonize the gas grid and reach net zero. So we really need to come together to this challenge, and I'm pretty sure we will do that. So thank you for your time. Yes.
Take a seat. And I'm sure we're going to have some questions. I'm going to ask a couple of online ones first, if that's all right. But do keep thinking if you've got some questions. So, Gabriele, are other national measurement institutes currently active in CCUS? So, have a drink of water first, of course. After all that was a fantastic presentation. No, great presentation. So, any other national measurement institutes currently active in CCUS?
Well,
At the minute, again, there is a bit of gap there, honestly speaking. There are good intention. There are different players trying to develop facilities, but especially on the liquid part, I would say there's not really a clear commitment and a clean investment decision. So yeah, we really need to address that as soon as possible.
Okay, with some urgency. Another question, is two-phase flow likely to occur at the metering point?
Yeah, that's probably a good question. Whatever I spoke with the operators, they don't want to have two-phase flow. That's out of question, you know, because it will really affect the performance of your meter. So they're really designed for single-phase flow. Having said that, things happen. So yeah, we will see. It might happen that you will have some gas with small amount of liquid or some liquid with small amount of bubbles. So I think it's wise to think about that. Probably will not be the main concern now, I would say, but it probably will come at a certain point. Yeah.
Okay, and then one more, are standards or best practice guides available for CO2 flow measurement?
Not really. Yeah, again, that's another important key piece. Yeah, we need standards. We need regulation. We need standards, and otherwise things are not going to work. But you know, you see in the oil and gas industry, in any industry, standards are there, have been developed. I think we will get there with CO2 and hydrogen as well. We just need to develop these standards.
Okay, audience, do we have any questions? Okay, we've got one from Martin. We bring this over to you.
Thank you. Martin Hanson, Technical Director at NEL. Just to follow on, really, just to make a point rather than a question, just to follow on from what Gabrielle said, this is why, as the designated Institute for Flow in the UK, part of the National Measurement System, we're doing the work that we're doing and why we're doing it now, because there does need to be guidance on good practice. There does need to be standardization that works for industry. And at the moment, this is very much a perhaps not even fledgling industry. It's probably still somewhere within the egg. But if we don't put these things in place, then it's certainly going to slow down the rate at which CCUS can be implemented. And so this is really why we're diverting our existing NMS funds to support this area at this time.
Hi, I'm Lewis Johnson from Kettle Engineering, and I was just wondering what process conditions you're focusing on for your hydrogen in your stage 3 and CO2 in stage 4.
You mean for the CARB project, the European
Yeah,
project?
yep.
Yeah. Well, that's under investigation now. As I was saying, we are looking to reach stakeholders. We are reaching stakeholders at the minute. We really want to know what they want. So what the gas grid wants, you know, we have indications, but I don't want to say anything. I don't want to nail down condition now. We are still investigating that. But if you have some condition you would like to, then yeah, let me know. we are getting all of them, and then you know, sum them up.
Okay, thank you.
Hi, Craig Marshall from McMenan. I think you may have just answered this question, but from your operating envelope of the proposed liquid facility, it looks like the operating envelope crosses over the phase boundaries from liquid, gas, and supercritical. Do you expect that meters are going to be used in operation where they could experience potentially one of the three? Or do you expect it to be this meter's designed and tested for the dense phase CO2 only?
Yeah, again, I think the perspective is to stay with one phase as much as you can. You don't want to cross the boundaries at all. But I didn't touch it, but there is a big unknown which is called impurities. And when you start to add impurities, strange things can happen. Of course, we will research them. We will have a question of state. But again, during operation, it might happen if you are maybe for certain specific condition, a shutdown or whatever. You may happen you have kind of a transition. But again, I think operators are really trying to have a safety boundaries to stay away as much as possible for any phase transition.
Thank you very much for that. We've just got one question. Chris has got one he wants to ask too.
More around what you think the target uncertainty is likely to be, and then how that will influence the facilities, the gas and the liquid facilities.
Well, yeah, that's a very good question. That's key, you know, uncertainty. Yeah. Again, I think it will be probably relevant to nail this down in some kind of regulation or standard first. That's probably needed. There should be some input on that regards. At the minute, people, as far as I know, are going with EU ETS, the EU Emission Trading Scheme, which it says around 2.5%. But I know that a lot of people are already looking for developing things for 1.5. You know, yeah, we don't know what will happen in the future, but it may be that also this threshold will lower with time, especially if the carbon price goes up. But at the minute, I think is in the region 2.5 and going down to 1.5. Yeah, I would say. Yeah. So the facility should be 4 or 5 times less than that, I would say. Yeah, as a rule of thumb.
Got one more online question here for you. Other than Coriolis meters, what other meter technology are you using for the decarbonised grid? You mentioned 8 meters being assessed.
Yes. Again, that's under discussion. We are reaching manufacturer and we are looking if they are willing to loan us meters for the test. So we are really open to any technology. I mean, the aim of this kind of exercise, as we were also discussing before, is to assess which is the best technology, not just saying this is the best. So yeah, any technology can be used in my view. It's good to test as many as possible. Of course, we have limitation in budget, time, so we will need to go down to a selection of them. But yeah, we will try to accommodate as much as possible.
Brilliant, thank you. Great presentation. That's great. So thanks very much, Gabriele. Now for our final guest. And like the first, like Revata, Dale is involved in hydrogen, but this time in heating. So, which apparently causes 1/3 of all greenhouse gas emissions. I'm sure most of you know that. So Dale Anderson is the gas networks lead at NEL. Thank you very much. He's building a test facility to see if hydrogen can be used in domestic gas meters. Now, it's thought to be the first of its kind in the world, at least we think that's the case. And he was actually on telly last night on Scottish TV because they came along and had a look at the plant. And also, I think some of you will be able to go and see it a bit later on. But Dale, if you can tell us all about it, that would be great.
Sure. Yep, so thanks for the introduction, Sonia. And as she says, I'll give an overview of our domestic gas meter test facility that we have designed, commissioned, built, and are now testing here at the National Engineering Lab. So first, I'll give you an overview of a bit on the requirement for the facility, so why we decided to build it in the first place. So it really stems from the need to decarbonise heating. As Sonia says, over 1/3 of greenhouse gas emissions in the UK is from heating. So that's predominantly space heating and also intensive industrial processes. And to meet our net zero requirement, there's a requirement to eliminate or at least significantly reduce natural gas usage for heating. Options to do this, so this can be low carbon electricity, hydrogen, bioenergy. So there are options. And I've taken a quote from the Clean Growth Transforming Heating paper by the Department of Business, Energy and Industrial Strategy. And it says, given the diversity of heat demand, no one solution can provide the best option for everyone. A mix of technologies and customer options will need to be available. So from that quote, it looks as if hydrogen is going to play some part. We don't know how big a part hydrogen will play for heating, but we recognise it's going to play some part. And that's reaffirmed really in the recently published hydrogen strategy by the government. I won't read this quote word for word, but it essentially says there's a lot of work to do to develop evidence on the costs, benefits, safety, feasibility, and this decade will be particularly critical to understand hydrogen's role. And there's a need for everyone to work together on studies, tests and projects to view whether hydrogen is a viable solution for heating. Work is already underway in this area, so there are lots of demonstration projects popping around. So there's the HyDeploy project, where they're looking at blending up to 20% hydrogen into the gas grid. There's a Hy4Heat project looking at new appliances for 100% hydrogen. The H105 project is going to be supplying homes with 100% hydrogen, several hundred homes and even beyond that. Other projects such as HNet Northwest, H21, this list is by no means exhaustive, but there is a lot of work going on to see whether this is feasible and using hydrogen in the gas grid is feasible. So that takes us on to the meters that sit outside everyone's homes. So they currently meter natural gas. How do these perform in hydrogen or natural gas hydrogen blends? Is the accuracy affected? Or do we need to develop new meters to be used for hydrogen? In recognising this, this is what BEIS recognised and subsequently funded us to build a hydrogen domestic gas metering test facility here in East Kilbride. So to answer these questions, essentially. Now the design and operation of the facility. So I've got a few slides on this. For those that are going on the tour, I'll go over it in more detail and it will be nice to see it after this as well. So before I go on and show further slides on complexities of the facility, it's pretty simple in operation. It's an open flow loop. We have two separate lines to meter methane and nitrogen and a line for hydrogen. We can operate with single gases, so we can measure pure methane or pure nitrogen. We can also measure pure hydrogen. And we can also measure blends of methane and nitrogen and hydrogen. We measure the reference flow rate separately for each of the gases. And then if we're testing a mixture, they will mix after we measure the reference flow rate and then pass through the test meter and then out through the vent. And we essentially compare a reference flow rate to what the meter outputs. For our reference flow rates, we use sonic nozzles for a reference metering. These are relatively simple construction, and we can, by measuring upstream temperature and pressure, you can calculate the mass flow rate from the appropriate thermodynamic properties of the fluid. Provided they're calibrated against the appropriate primary standards, you can achieve very low measurement uncertainty with these, and it says approximately 0.2% with air. You can get them in a wide range of sizes, so that means a wide range of flow rates, and also our nozzles are calibrated in air, but the performance is consistent when operated in hydrogen, and we've seen that. We couldn't actually get nozzles small enough to reach the lower end of the domestic range, so we purchased some laminar flow elements, and these are used for the lower hydrogen flow rates. These are similarly differential pressure devices, but they operate at laminar flow, and it's essentially a small bundle of tubes. And these laminar flow elements, it should say, were calibrated in hydrogen. So that's what's used for a reference instrumentation. So this is the facility in a bit more detail. We've got gas bottles of hydrogen and methane and a supply of nitrogen from the James Young building. So if we're measuring pure hydrogen, we've got gas bottles that sit outside. They'll be around 200 bar. We'll regulate down to about 16 bar in the cylinder store, and then the gas will be fed into the facility. That one. We've got 4 control valves in parallel, and this allows us to set the inlet flow rate and pressure to the flow nozzles or laminar flow elements. So we've got 3 flow nozzles in parallel and also 4 reference laminar flow elements, and we'll essentially choose the one that's appropriate for the flow rate. So it will then pass through the reference flow rate devices and then subsequently through a heat exchanger, which can condition it to, I think, down to -25 and up to 40 degrees C, through a static mixer, and then subsequently through the meter under test, and then out through the vent. The other side is similar for methane. So again, it's regulated down from 200 bar down to around 16 bar. We've got some inlet flow control valves which set the inlet pressure and flow rate, and we will choose one of the 4 appropriate nozzles. So these are different size nozzles based on the flow rate we're testing at. They'll pass through there and then through the test section. If we're testing with mixed gases, these 2 gases will mix here, pass through the heat exchanger. We have a static mixer, and then we'll go through the meter under test and then out through the vent. So it's essentially, it's just a big open loop. The gas comes in via the cylinder store, and actually the process vent line actually vents at the cylinder store as well. So it goes outside, inside, and then back outside again. So our gas is supplied from here on the left-hand side in our cylinder cage. So the gas is in the bottles here and it's regulated down. It's then fed along the side of the building, and then our test facility sits inside. It's all welded pipe into the building to minimise leakage. And the control cabin and test section of the facility are actually inside. So when we go inside, the main body of the facility is actually in a room within the room. This is an ATEX rated enclosure. All the valves, etc., and the control of the facility is done via a room externally to this using a SCADA screen. So you can see someone operating the SCADA screen at the minute. So that's how we do our testing. As we are operating with hydrogen and methane, flammable and explosive gases, so we do have to take precautions. So everything in there is ATEX rated. We close off the gas supplies if we open the enclosure door. We've got an LEV extraction fan, and we also operate the rig in a slight negative pressure so that if gas is flowing one way, it will flow into the facility and we won't have any gas flowing out of it. And we also have gas detection systems as well. So if we detect too high levels of hydrogen, methane, or a low oxygen content, the gas supplies will automatically switch off. So that's a design specification of the facility there. So the flow rates essentially cover the domestic gas meter range. So down below 1 standard meter cube per hour, up to around 6 for a typical sized domestic gas meter, but our range does extend beyond that. So up to 16 for methane, 42 for nitrogen, and 50 for hydrogen methane. We do envisage that the methane will increase. That is just due to Joule-Thomson effects and actually freezing regulators. But we do envisage that flow rate will increase. So the facility, this is the main body of the facility on the right here. The gas actually enters. How do you work? All right. The gas enters, so from the cylinder store, we've got our methane line and hydrogen lines here. And then it enters. This is just a coiled bath heat exchanger. It's just got water in it, just to bring it down to closer to room conditions if it's cold in the winter. So our hydrogen section's here on the left. So the gas goes up. There's 4 control valves here. It takes a sharp left turn and then flows from left to right through one of the appropriate devices. So that's our 4 laminar flow elements and 3 nozzles. Valves will be opened next to these depending on which flow rate we're testing at. The nitrogen will exit here as well, but that will flow further along. It will flow up through the control valves, take a sharp right turn, flow up and flow through the appropriate critical flow nozzle. If we're operating with a mixed gas, both of these will be operating at once. The gas will mix at the middle, it will turn round, it will go down through a heat exchanger, which is actually using heat exchanger fluid this time, so we can control the temperature a bit better through the insulated piping. And then we'll have the test meter here. We'll pass gas through the test meters after it goes through the reference section, and then out through and back through the building and to the cylinder store. So we have did some testing with this facility. We did quite an extensive bit of testing for the HyDeploy project that I mentioned before in the slides before. So a bit more on the HyDeploy project. This is a UK demonstration project looking at to prove that blending up to 20% volume of hydrogen with natural gas is safe, and it's a greener alternative to use 100% natural gas. It's a project led by Cadent, but there's a consortium, so there's Progressive Energy, Northern Gas Networks, Keele University, the Health and Safety Executive and IT Empower, and government are providing extensive funding for this. And essentially the main purpose of the project is providing evidence that existing pipeline components, domestic appliances can work with this 20% hydrogen blend. So currently at the site, 100 homes and buildings are being supplied by the blend. No one's really noticed any disruption to service, and there's been positive feedback by students and university staff. It's allowed them to do durability testing on boilers and other appliances, and that phase of work finished in spring this year. So they are looking at further phases of work on larger demonstration networks for public networks, northeast of England and the northwest. The reason for our involvement, they contacted us with respect to the gas meters. So you want the consumers, both from a technical perspective, but also from a consumer confidence perspective, they wanted consumers to know that actually they're getting what they pay for as the gas passes through the meter. So understanding that, we developed a test matrix. So we tested 18 domestic gas meters. So we tested 11 diaphragm meters. So that's by far the most commonly used in the UK. These are just volumetric meters that essentially expand and contract as gas fills through them. Tested ultrasonic meters, 5 of them in thermal mass. So the identifiers here refer to a particular model. So we tried to test at least 2 of every model. We tested 6 of the 1 diaphragm meter model because we tested 2 new. We tested 2 that have been used to measure over 10,000 meters cubed of natural gas, and those that have used a blend over 10,000 meters cubed, just to see if we see any differences in the performance of them. Ultrasonic meters, we tested 2 new meters that had been designed for hydrogen blends, but also we tested those that have been in the gas networks for over 20 years, just to see what the performance looks like for those. And then as well, we included 2 new thermal mass meters in the programme. And the point of this work was, if we pass natural gas through it, what do the results look like? If we pass a blend through it, what do the results look like? And what's the difference? And what do we think is going on? So we did that for every meter. Go back. So we tested 10 G4 type diaphragm meters. So these are G4 diaphragm meters have a maximum flow rate of 6 meters cubed per hour. I've only included one graph here because the results were almost the same for every one we tested, all 10 we tested. They may have slightly different slopes to the error curve, some may be flatter. All of them performed within the mid accuracy class 1.5, so that is the accuracy requirements for a meter to become Measurement Instrument Directive certified. And all of the 10 G4 meters performed within there. But more importantly, the results were on top of each other for every diaphragm meter we tested. There was no significant difference between the 100% methane and the 80-20% blend of the gases. We tested 1 larger diaphragm meter, so that's a Qmax of 60 meters cubed per hour. It performed well, but didn't perform as great. It didn't meet the accuracy class requirements for the 80-20% blend, and it separated a little bit more here, but generally the results were pretty close. I mean, it was less than 1%, significantly less than 1% difference between the blended gas and the 100% methane. So overall, the results for the diaphragm meters were pretty good, and they confirmed that essentially that they are metering to a sufficient accuracy, shall we say, for the blends. We tested 2 new ultrasonic meters as well, and again, for the higher flow rates, they performed pretty well. All of the results are within the mid accuracy class limits, which is good. But we did see a bit of separation with them, but these are more intrinsically complicated meters. So they've got internal calculations, and probably because of fluid property calculations, you do see a bit of separation here at the lower flow rates. But again, we were all within the accuracy class limits. This was an older meter. This was installed in 1997, and we tested this with methane in the blend as well. It looks as though the meter has poorer repeatability, but the reason for that is we had no means of putting the meter into test mode and sampling from it. So we actually had to take a video camera and take a camera of the digital display. The digital display only updated every few seconds, so it was difficult to determine actually when the number was changing on the meter. We could reduce this repeatability by taking very, very long test points, but we knew that the repeatability issue was because of the sampling mode that we selected. Strangely though, the methane at the lower flow rates showed poorer repeatability, which can't be explained by just the test method, because the blend seemed to show good results. We are not sure why this is. Again, all errors were within the mid-accuracy class limits, but we seem to have poorer repeatability for the methane for this meter. I'm not really too sure why that is. These are two other older ultrasonic meters of the same model. These results are quite interesting. So it seemed as if for some flow rates, the results seem to agree. Again, we've got this scatter again because of the logging method. We had to use a video camera and we didn't put it into test mode. We could reduce the repeatability for, say, these points if we took longer test points. We know that. But just randomly here, it was as if the meter would just jump and the repeatability looked very poor. So what we did is we decided to test with 15 and 10% hydrogen just to see what the results looked like. Go back. And they were more in line with the pure methane for meter G2. So we were wondering whether it may be that the fluid properties are almost just tipping over the meter at that point. So they seem to work for pure methane 10 and 15%, but when we get to 20%, whether the meter just reaches its tipping point, essentially. Finally, I've included two thermal mass meter results. Again, these results agreed pretty well. We had poor repeatability for the blends, and also at lower flow rates, there seemed to be a sort of difference in the results between some of the test points. And the mid-accuracy requirements, it requires test points not to have a difference of more than 1% from the same flow rate. So this meter actually fails for a few of the flow rates because of the errors for the same flow rate are greater than 1%. But at higher flow rates, the results, although there are some differences, they generally agree quite well, and it performs quite well apart from that. So we tested a total of 18 gas meters, 11 diaphragm, 5 ultrasonic and 2 thermal mass. Diaphragm meter results were very good. They're the most simplistic of technology, where they're measuring the volume passing through it. So it was, in a sense, sort of expected, but we were wondering whether introduction of hydrogen may cause increased leakages or anything like that, but it didn't seem to. So the methane and blend results generally agreed within 0.3%. Only one meter, and that's the larger B10 diaphragm meter, actually exceeded the class 1.5 maximum permissible error limits. It says the durability effects were not studied in detail, but the 2 meters, which were previously metered over 10,000 meters cubed of gas, had errors consistent with other meters of the same model. To really assess durability, we should probably, or we should use the same meter before and after testing, because these are different meters we've tested, the new meter and the meter that's been subjected to that, so we don't know what the shift is in performance. Ultrasonic, so the new meters, the results were within 1.5 error, and the errors for the methane and the blend agreed at higher flow rates within 0.3%, but at lower flow rates we've seen that sort of separation. F1, which was the first of the older meters, that was a meter installed in 1997, that performed pretty well, considering the age of the meter. We did see shifts in behaviour for G1 and G2, but when we tested with the 10 and 15% blend, we didn't see this, so we're wondering whether this may be a function of, the fluid property calc, the internal calcs of the meter. But that was of similar aging condition to F1. Thermal mass, again, they were all within the class 1.5 maximum permissible error. Slight greater scatter for the blend, and some points with the blend didn't meet the mid-stability criteria, so difference in errors of more than 1% for the lower flow rates there. Again, as it says, the agreement, there is an agreement usually within about 0.5%, but at certain flow rates we've seen it was worse, but the errors just seem to jump down or up the way. And I think the summary, overall the results are pretty good. Several flow meter models, particularly the diaphragm meters, perform consistently with the methane and hydrogen blend.
Thank you very much. We'll take the microphone back off. You've got Quite a few questions. That's great news. And as you're sitting down, first one for you is, are any other methane or hydrogen blends currently under investigation? And in fact, supplementary to that, is 50-50% ever going to be an option?
So the HSE did a report back in the 90s to say that up to 20% can be blended safely without any disruption, and all the appliances that have been installed in homes, etc., since 1996 can take up to 23% hydrogen. So any more than that, I think you need to start converting things. So it's minimal disruption, up to 20%.
Before I throw it out, what is done for relative humidity measurements in the facility?
We use pure bottled gas.
Okay.
Yeah, so we use relatively pure methane and hydrogen. It's research grade. So that's why we use methane as opposed to natural gas in terms of impurities, because we need to calculate the thermodynamic properties for the reference flow rates pretty accurately. That was the question, yeah.
So yes, I think so. What sort of standards do you follow for reference critical flow or laminar flow measurements?
Standards.
Does that make sense? For reference to critical
There are
flow?
standards. There's the ISO and yes, for critical flow, but that is if they are manufactured to a specific tolerance. You
Right.
don't need to calibrate them. But ours have been manufactured and calibrated, and we have calculated the uncertainty, etc., from
Okay.
them. So, yeah.
Okay, and one more. What sort of simplifying assumptions can be made given the low pressure? Make sense to you? No? Okay. Okay, no worries. So, oh, actually, there's one more here. Again, don't know. When can we expect the results of the facility into comparison? Question.
Possibly next summer.
Okay.
We're doing a comparison study with some labs in Europe looking at our facility and others, and the transfer package has been manufactured, so we'll be able to see how the facility stacks up against other NMIs. So hopefully the work's due to be completed at the start of next year, so hopefully by the end of the following year there'll be a journal article, etc., on the comparison study.
Hopefully that answers the online question there. I have got one for Martin, actually, which I'm going to read here and then hand him the mic, and then we'll take some questions from the floor as well. So this is one for Martin in the audience, and I'll take the mic over to him. What are your thoughts on hydrogen's role in domestic heating being limited to energy storage at an industrial scale, converted to electricity for online demand deployment to the domestic market through the existing grid, being used by already available electrically powered domestic appliances? So, long question. Martin, but I'll hand this over to you.
Okay, thank you, Sonia. I'll attempt to give not too long an answer to that one. Yes, there is currently a great deal of debate within the UK about the role of hydrogen in heating. We saw the government release the hydrogen strategy over the summer, late summer, and that was followed up a few weeks ago by the heat in buildings strategy. There is a very clear drive towards the use of heat pumps for electrical heating of homes, and there are many attractions to that approach. With a heat pump, you've got an energy multiplier, so you're obviously taking heat from the ground or the air, depending if it's air or ground source heat pump. And so the electrical energy you put in to run the pump is usually magnified 2.5 is a good rule of thumb. And so certainly I think it's correct that in the future we'll see a lot more use of heat pumps in homes. However, it's worth bearing in mind that at the moment 85% of homes in the UK are heated by gas. It's also worth bearing in mind that if we look at the demand for end-use heat, there's two ways in which that varies. One is on a daily basis. So first thing in the morning, most people's boilers come on and your house is nice and toasty when you get out of bed. So there's a very big ramp up there, which the gas grid deals with rather uniquely through what's called line pack. So the entire gas network is pressurized up overnight, and in the morning when all the boilers kick in, there's a huge energy store that's used, and the significance of that, it should not be underestimated. That's a vast amount of energy that ramps up very, very quickly every morning. You've then got a longer cycle of periodicity in terms of seasonal between summer and winter, which again, it's difficult with electricity to store electricity on a very large scale and longer term, i.e. more than days. Whereas with using hydrogen, you can store in the same way that you do with fossil fuels today. With hydrogen, you can store that longer term for intra-seasonal storage, and you can store it at scale. So I think there is definitely a role for hydrogen in heating going forwards. As Dale set out, there's a lot of gas network projects looking at this at the moment. The heat and building strategy and the hydrogen strategy make very clear that the government would like to look at this more closely in the next few years. And there's certainly a suggestion that hydrogen into the gas networks may be more preferable in some parts of the UK than others. So we'll see how that goes. It's also the fact that, as Dale alluded to, it's not just about home heating. For heavy industry, there's certain things where you need direct flame heating, and you cannot replace that, unfortunately, with electrification. So that's another good example of somewhere where hydrogen is effectively complementary to electrification, and hydrogen would have a role to play. So I hope that answers the question.
Hi, Gareth Lake from Solve Limited. So my question was about the uncertainty of the test facility.
Yep.
I saw your slide there, I think 0.3% on hydrogen and 0.5% on methane. I was wondering what contribution of those percentages is from the metering versus some kind of compressibility value.
Most of the uncertainty is from the calibration of the nozzles. So we had our nozzles calibrated externally, and also the critical flow factor. So as I said in the slide, it shows 0.3% for hydrogen and 0.2 for nitrogen, I think. So the additional uncertainty for hydrogen is due to the critical flow factor, and also main body of the uncertainty is from the calibration. So ours were calibrated in air. So that leads on to, we're looking to build a primary standard which will calibrate these nozzles in the gases they are actually being tested in, which will further reduce the uncertainty. So most of the uncertainty is from the calibration of the nozzles themselves, which were done externally, and we don't have the capability yet. But BEIS is funding a primary standard as part of the flow programme, which we've built here in East Kilbride. We'll essentially take the nozzles out of the facility, calibrate them in a primary standard in the relevant gases, and then put them back in the facility, and that will drive down their uncertainty.
Just to follow up, I noticed, well, the uncertainty on methane was slightly higher than that on hydrogen. What contributed to that? Was it just the equipment?
No, it's historical. From research papers we've read, it's looking at the type of gas that's passing through the nozzle, and at lower flow rates, I believe, because methane is a different molecule, nitrogen and hydrogen are both diatomic molecules, and you get different effects as the gas is flowing through the nozzle, and we are less certain on the transferability of the calibration from air to methane is what we are for air, which is mostly nitrogen. So air and nitrogen we're pretty confident with. Hydrogen, a diatomic molecule, and we think the effects are similar. And from comparisons that we've did using meters, we have confidence in that, and we are soon developing more confidence in methane, but we're conservative and we put 0.5 up for methane. We hope to look, that is something we hope to look at with a primary standard and actually calibrate it in methane, in air, in hydrogen and nitrogen, just to see what the differences are in terms of the curve for the sonic nozzles.
Thanks, that's really interesting.
follow-up questions? I know we asked a few afterwards. Any hands up there at the back? We've sort of slightly overrun on time. I'm just going to ask one very brief question that's just come in for Dale. Why was the test rig designed to vent gas and not use a circulation loop?
A few reasons. Flow stability, so we weren't sure we could achieve the appropriate flow stability and therefore the uncertainty. And then also, this was before I joined the organisation, but I think there was a difficulty in getting compressors for hydrogen service for our requirements. And then a third reason is the volume of gas we're passing through this isn't a lot. If we had to install a compressor system, it would significantly increase the cost of the facility itself. If we're operating with blends, how do you separate the blends out? Back to hydrogen gas again. It's just a cleaner system. The disadvantage is we use gas and we put gas through a vent, hydrogen, methane, which isn't ideal. But again, it comes back to the issue in the primary standard for vehicles, the refueling standard where we vent gas. It's just not economically, it's not achievable for the budget. And the amount of gas that's passing through is really minimal. We don't test all day. It takes a few hours to test a meter. So that's the reason why.
Okay, thank you very much for that. And thank you all our panelists. I think you'll all agree some excellent information there that we've learned about this morning. And for anyone online, any questions we haven't got to, we will attempt to get back to you via email. So if we haven't covered everything, we are out of time now. Thank you so much, real audience, for being here and putting some questions. And great. I mean, it's going to take us a while to transition into clean fuels, but good to see there's some expertise here, you know, that's going to help us get there. So yeah, thank you very much from me too. So great. You are free to go and join your tour. If anyone's going to have a look at the hydrogen gas meter facility, then feel free to do. I think that's being arranged now. That's right, Ian?
So, who's